Hello everyone. What we'd like to do in this video is just do some more examples of using the rational roots theorem to factor polynomials. Let's do our first example. So let's say we have the polynomial p of x, which is equal to, let's say, x to the fourth plus 7x cubed plus, let's say we have a 17x squared plus, how about a 17x plus 6. We're going to try to factor a fourth degree polynomial. Okay, so go ahead and pause the video and try this one on your own. Okay, so there's actually a tip that I want to give you in these type of problems. What we want to be careful about is multiplicity of zeros. So I'll show you what I mean here. So let's first of all write down our candidates of possible zeros. Okay, so notice here that this is a 1, so the denominator of my possible rational roots will always be a 1. So I can really just look at the factors of the constant term 6. So my list of possible roots, we could have plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So let's start checking these. So let's start with 1. So we'll have a 1. So a 1, a 7, a 17, a 1, 7, 17, 17, and a 6. Okay, let's start checking. So we'll get a 1. 1 times 1 is 1. 1 plus 7 is 8. 1 times 8 is 8. 8 and 17, what is that going to make? That's going to make 25. Okay, and then we are going to get 1 times 25. We're going to get a 25. I can almost see right off the bat. I can see right off the bat that when these add together, I'm going to get a bigger number here, and it's not going to be negative 6, and that's not going to work. Let's actually kind of pause here and just actually look for a second at this polynomial. So before I even started checking 1, notice that every single one of these terms is positive. So whenever I plug in a positive number into here, it's always going to output something positive. So actually just looking at this, this is telling me that this polynomial, it actually can't have any positive roots. They actually have to be negative. When I plug in a negative number and I take a negative number and I cube it, it'll be negative. So I need negatives to possibly cancel things out to get out of 0. So right off the bat, just looking at this one, I know that none of the positives could possibly work. So actually I've cut my list in half just by kind of thinking about it for a second. So let's check out negative 1. Let's check out negative 1. Okay, so 1, 7, 17, 17, and 6. Okay, so let's drop down this 1. Okay, so negative 1 times 1 is negative 1. Negative 1 plus 7 is 6. Negative 1 times 6 is negative 6. Negative 6 plus 17, that'll give us an 11. Negative 1 times 11 is negative 11. 17 plus negative 11 is 6. And negative 1 times 6 is negative 6. These add to give us 0. So I have a remainder of 0. So that means that x plus 1 is a factor of this polynomial, or x equals negative 1 as a root. Now, here's something I want to talk about. We actually cannot just cross off negative 1 from our list yet. Now, just take a second and think about, why can I not cross negative 1 off our possible list quite yet? The answer is because the root x equals negative 1 could have a multiplicity bigger than 1. It could have a multiplicity of 2. It could have a multiplicity of 3. So x plus 1 could go into this polynomial more than once. So we don't want to cross it off unless we check multiplicity. So does x equal negative 1 have a bigger multiplicity? Does it have a multiplicity of 2? Well, let's just check. And just to kind of make a note here is already I know that this polynomial p of x is equal to what? That'll be x plus 1 as a factor, and I'm going to get an x squared plus 6x. I'm sorry, x cubed. This will be x cubed plus 6x squared plus 11x plus 6. So if x plus 1 goes into this polynomial more than one time, it means that x plus 1, if it has a multiplicity of 2, would go into this polynomial. So I'm just going to continue the synthetic division using this polynomial now. I just want to break this piece down further. Well, I already have those coefficients lined up right here, so let's just continue the synthetic division. So does it have a multiplicity of 1, or does it have a multiplicity of 2? Let's check. Let's drop down the 1. Negative 1 times 1, that's negative 1. 5 plus negative, 6 plus negative 1 is a 5. Negative 1 times 5, what do we get out? We get out negative 5. 11 take away 5 is 6. And oh my goodness, negative 1 times 6, I get out a negative 6. Yes! Yes, it did have a multiplicity of 2. So x plus 1 goes into this polynomial twice. Okay, so what do we have? What do we have? We now have this polynomial, p of x. Well, x plus 1 is a factor, and it goes into this polynomial twice. Okay, you could check it again if you want, but now I'm down to a quadratic. X squared plus 5x plus 6, and now I can factor this from here. So this will be x plus 1. Okay, what am I going to get here? I think I'm going to get x plus 2 times x plus 3 squared here. So notice that x equals negative 1 as a root with a multiplicity of 2. X equals negative 2 as a root, and x equals negative 3 as a root. Notice that all of its roots had to be negative, which is an observation that we made here. So go ahead and, I won't graph it here, but on your own, go ahead and graph this polynomial. Or maybe let's just do it real quick. Yeah, let's just do it real quick. It shouldn't take us too long. It shouldn't take us too long to do. Let's do it. Okay. Okay, so it has n behavior next to the fourth, so here's our n behavior. Okay, it has roots at negative 1. It has roots at negative 1. Oh, over here is negative. It has a root at negative 1, negative 2, and negative 3. Okay, and it has a y-intercept. If I plug in 0, I get an output of 6. So it has a y-intercept of 6. Okay, so let's see what happens. Okay, well, x equals negative 3. That root has a multiplicity of 1, so it'll cross through. For negative 2, it also has a multiplicity of 1, so it's going to have to cross through. But x equals negative 1 has a multiplicity of 2, so it's going to bounce off negative 1, cross through negative 6, and it's going to connect with my n behavior, which makes us feel good that we're doing something right. So here's the graph of this polynomial. Okay, I'm going to have you do an example. Let's do another one. Okay. Let's try. How about x to the 4th minus 4x cubed minus 5x squared plus 36x minus 36. Okay, go ahead and pause the video and try this one out on your own. Okay, so again, let's try to figure out our candidates for the roots. Okay, we have a coefficient of 1, so I only need to look at the multiples of the constant term. So our candidates are plus or minus 1, plus or minus 2, 3 goes in there, so plus or minus 3. You know, what might help us here is just taking a look at 36 itself. Okay, so I could have a 1 and a 36. I could have a 2, and what if I cut that and have a 2 and an 18? I could have a 3 and a 9. I could have a 3 and a 12. 3 and a 12. We could have a 4 and a 9. 5 doesn't go in there. 6 goes in there. A 6 and a 6. 7 doesn't go in there. 8 doesn't go in there. 9 goes. So now I'm just repeating myself. So here are our list of all possible factors. So we could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6. We could get plus or minus 9, plus or minus 12, plus or minus 18, or plus or minus 36. Plus or minus 36. Just making sure I wasn't in that glare. Okay. So you can start checking these. For the sake of time, you'll actually find that x equals plus or minus 1, you'll find that these ones don't work. So you can check that on your own. But you'll find that these ones don't work. Okay. Better red one. You'll find that these ones don't work. Okay. We should find that 2 works. 1, -4, -5, 36, and -36. So if we bring down the 1, 2 times 1 is 2. 2 plus -4 is -2. We'll get a -4. Looks like we'll get out a -9. 2 and -9, what is that? -18. -18. 36 take away 18 is 18. 2 times 18 is positive 36. Sweet. So 2 is a root. Okay. Does it have a multiplicity of 2? I don't want to cross that off our list yet, so let's check if it has a multiplicity of 2. Okay. Let's drop down the 1. 2 times 1 is 2. 2 plus -2 is 0. 2 times 0 is 0. -9 plus 0 is -9. 2 times -9 is 18. 2 times, -18, sweet. So I get out 0. So it does have a multiplicity of 2. This won't always work, but we always want to check multiplicities if possible. Okay, so how does this polynomial break down? Notice I'm actually going to stop checking here because, well, this is now a quadratic. So this polynomial p of x, that's going to factor to, well, we discovered that 2, that the root 2 has a multiplicity of 2, so x minus 2 goes under there twice. And I'm left with an x squared. This would be an x squared, if you like, plus a 0x minus 9. Or this is x minus 2 squared. And now this will just be x squared minus 9. So this is a difference of squares. So this will be an x minus 2 times an x minus 3 times an x plus 3. So we fully factored this polynomial. Oh, squared. Got the squared. Okay. So let's go ahead and factor this really quick. I'm sorry, let's graph it really quick. Okay. Okay, this polynomial will have an end behavior like a quadratic. Okay, a happy face quadratic. Okay, it has a root at 2. Has a root at 2. It has a root at 3. And it has a root at -3. And it has a y-intercept of -36. So I'll just write -36 here. Okay. So the root x equals -3 has a multiplicity of 1, so it'll cross through. It pretty much has to cross through, so it hits the y-intercept. Okay. 2 has a multiplicity, x equals 2 has a multiplicity of 2, so it'll bounce. And now it better cross through. The root x equals 3 has a multiplicity of 1, it'll cross through and match up. Beautiful. There we go. There's our graph. Okay, again, I've said this before, I don't necessarily know the relative heights of these humps here. Again, we just want to draw loose sketches of these polynomials. Okay. Let's do some examples. Notice that every time we've used the rational roots theorem, we've never really picked a root out that was a fraction or used synthetic division with fractions. So let's do some examples like that. Okay. So let's try. Let's say we have a 3x cubed minus a 13x squared plus a 7x minus a 1. Go ahead and pause the video and give this a shot on your own. Okay. So notice that in this example, my leading coefficient is not a 1. So let's find our possible rational roots. So for the numerator will come from factors of -1. Okay. And the 3, the denominator will be the possible factors of 3. Okay, so I could have a plus or minus 1, or I could get a plus or minus 1 here, or a plus or minus 3. So our possible combinations with 1 as a denominator is just 1 times 1. So our lists will have an x could be plus or minus 1. Or I should possibly get plus or minus 1/3. Or plus or minus 1/3. So here are our list of our possible rational roots. So let's use synthetic division to check which ones are roots. So 3, -13, 7, and -1. Okay. So let's check out 1. Okay, with 1, we'll do 3. Okay, 1 times 3 is 3. I'll get a -10. I can almost see that this isn't going to work. I'm going to get a -10. Here I'll get a -3. I'm not going to get a +1 here. So 1 doesn't work. Let's try -1. Let's try -1. Okay, so I'll get a -3. I'm going to get a -16. I'll get a +16. I can already see this isn't going to work. Okay, so -1 doesn't work either. Okay, let's try 1/3. Let's try 1/3. Okay, we'll bring down the 3. 1/3 times 3 is a 1. So -13 plus 1, I'm going to get out a -12. 1/3 times -12, well, that gives us a -4. 7 plus -4 is a 3, and 1/3 times 3 is a +1. Sweet! So we have a remainder of 0. So that means that x minus 1/3 is a factor of this polynomial. Okay. So this polynomial p of x, okay, this is going to factor to an x minus 1/3 times, we'll get a 3x squared. We'll get a 3x squared minus a 12x plus a 3. So now what I want to do is I just want to try to factor this polynomial right here. Or we'll at least try to find the roots of this polynomial. Okay. So the first thing I'm going to do here, the first thing I'm going to notice is that I can factor a 3 out of these parentheses. So I'm going to go ahead and factor out a 3. What would I be left with? I'm going to be left with x squared minus 4x plus 1. It's just going to be easier to work with. Now what actually might be convenient just to make this look prettier is I factored a 3 out of these parentheses, but I could distribute it into the other parentheses if I wanted to. So we would have actually a 3x minus 1, which I think looks a lot nicer. Okay. Times a x squared minus 4x plus 1. Okay, so let's go ahead and try to factor this if we can. But you should quickly realize that this actually doesn't factor nicely. Notice here, if you were trying to factor this, you would look at the constant term. You would try to find factors of the constant term that add to -4. The only factors of 1 are 1 in itself, and neither of those will add to -4. So what am I going to do? How am I going to figure out the other roots of this? Well, I just basically need to figure out, I'm going to write this up here. The last piece I need to figure out, I want to know another one of its roots, is I need to figure out when x squared minus 4x plus 1 equals 0. So you could use a completing the square method to find the solution to this. I'm just going to use the quadratic equation. -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so we have our a is 1, our b is -4, and our c is 1. Okay, so the solutions of this will be -b, so I'm going to get a -4 plus or minus the square root b squared. So I'm going to get a -4 squared minus 4. Our a is 1, and our c is 1, all over 2 times a, or 2 times 1. So let's see what we get. So it looks like I'm going to get a 4 plus or minus, okay, what am I going to get here? I'm going to get a 16, I'm going to get a 16 minus 4, I'm going to get out a 12. I'm going to get out a 12 here. I'm going to divide that all by 2. Now if you want, we can actually clean this up a little bit. So notice here that 12 the square root of 12, that's equal to the square root of 4 times 3. I can distribute the square root to multiplication. The square root of 4 is 2 times root 3. So this is equivalent to 2 root 3. So maybe I'll move it over here. Need more board space. So it looks like I have a 4 plus or minus. I'm just trying to make this look as pretty as possible. So 2 times the square root of 3 all over 2. You can either think about factoring out a 2 and canceling it with this 2, or distributing the 2 to each one of these two terms. But this is going to reduce to 2 plus or minus root 3. So I actually know all of the roots of this polynomial. One of the roots is 1/3. This is our rational root that we picked up. But notice that we got 2 extra roots that are not rational. We had another root, which was 2 plus the square root of 3, and another root, which was 2 minus the square root of 3. So when using the rational roots theorem, it'll only possibly pick up the rational roots, and sometimes we might have to use the quadratic equation to figure out the roots that are non-rational. So in this case here, I'm actually, it depends what the book wants you to do, but if the book doesn't want you to continue factoring this, you could just leave it like this. We actually know what the roots are. We could figure out approximately what these are, and we could graph this. But let's say if we were to factor this completely, so we have a 3x minus 1. Okay. So since this is a root, since x equals 2 plus root 3 is a root, and x minus a 2 plus root 3 would be another one of its factors. And another one of its factors would be x minus a 2 minus the square root of 3. Why? Well, if I plug in 2 plus root 3 into here, 2 plus root 3 minus 2 plus root 3, that'll zero this out. Similarly, if I plug in 2 minus root 3 here, 2 minus root 3 minus 2 minus root 3, taking the same thing and I'm subtracting it from itself, I'll get out 0. So here are all of our roots, and we factored it completely. Okay, let's do one more example. Let's try and factor a 5th degree polynomial, or find all the roots of a 5th degree polynomial. So this will be our last example. Okay. Let's say we have a 2 times x to the 5th minus a 5x to the 4th minus an 18x cubed minus a 10x squared plus 4x plus 3. Go ahead and pause the video and try to find all the roots of this polynomial. Okay, so let's first find all the candidates for our possible rational roots. Okay, the numerator of our rational roots will come from the 3. And the denominator of our rational roots will come from the 2. Okay, so the factors of 3 could be plus or minus 1 and plus or minus 3. And I could get plus or minus 1 and plus or minus 2. Okay, so our possible list is I could get a 1 over 1. So I have a plus or minus 1. Or I have a plus or minus 3 over 1. I could also get a plus or minus 1/2. Or a plus or minus 3/2. So here's our list of our possible zeros, our possible rational zeros. Okay, so let's start checking them. Okay, 2, -5, -18, -10, 4, and a 3. Okay, let's check out 1. Let's see if 1 works. Okay. So 2, what do I get? A -3. -3, we'll get what? -21. I'll get a -21. I'm going to get a -31. I'm going to get a -31. I can see that this isn't going to work. Okay, so 1 will not be a root. Okay, let's try -1. Let's try -1. Okay. So we'll bring down the 2. I'm going to get a -2. I'll get a -7. I'll get a +7. Let's see what am I going to get here. I'm going to get I think a -11. I'll get a +11. I'll get a +1. Then I'll get a -1. I'll get a 3. And then yes, I'm going to get a -3 here. Those will add to give me 0. So -1 is a root, so x plus 1 is a root of, x plus 1 is a factor of this polynomial. Okay, does it have a multiplicity of 2? Let's check. Okay, so we'll bring down the 2. -1 times 2, I get out a -2. What are we going to get here? We'll get a -9. We'll get out a +9. Okay, 9, what are we going to get there? We'll get a -2. We'll get a +2 here. We'll get out a 3. -3, these add to be 0. So yes, it does have a multiplicity of 2. Okay, beautiful. Okay, so let's check if 3 and -3 work. Let's check if 3 and -3 work. So I'm just going to continue using synthetic division here. So if we want to check 3, see if 3 works. So 2, I'll get a 6, but I'll get out a -3. I'll get out a -9. I'm going to get out a -11. We can see this isn't going to work, so 3 won't work. How about -3? How about -3? Bring down the 2. I'll get out now a -6. -6, now I'm going to get out what? -15. And I'm going to get what? +45. I hope you can see. We can already see that this is definitely not going to work. Okay, so let's try, I don't know, how about 1/2? Let's try 1/2. Let's try 1/2. Okay, we'll bring down the 2. 2 times a half is a 1. 1 plus -9, we're going to get out a -8. 1/2 times -8, we'll get out a -4. -4 plus -2, we'll get out a -6. 1/2 times -6, oh yes. Oh yes, we're going to get out a -3. Those will add to be 0. Awesome. Awesome. So 1/2 is a root. And I've broken this down now to a quadratic, so I'm going to stop here and write down what we have so far. So what we have here is this polynomial p of x. It has -1 as a root, so x plus 2 is a factor. I'm sorry, x plus 1 is a factor. It has a multiplicity of 2. We saw that 1/2 is a root, so how about we write x minus 1/2. Okay, and what do we have left over? What we have left over is a 2x squared minus an 8x minus a 6. Okay. So now we just need to factor this polynomial right here. So what I'm going to do is I'm going to notice I can factor a 2 out of here. So we'll have an x plus 1 squared and x minus a 1/2. Okay, let's go ahead and factor out a 2. And I'll be left with what? I'm going to be left with an x squared minus a 4x minus a 3. And now, since I don't like this 1/2, what's nice is I can choose to distribute this 2 into this factor. So I'll be left with, this will be an x plus 1 squared. I'll then get a 2x minus 1. And I'm left with an x squared minus 4x minus 3. Okay, let's go ahead and try to factor this polynomial. Let's see, can we find factors of -3 that add to -4? Well, the only possible combinations for factors of 3 are 1 in itself, and one of them has to be negative. If one of them has to be negative, there's no way I can add these to get out a -4. So this will not factor nicely. We're going to want to use the quadratic equation to find the other roots. So when is x squared minus 4x minus 3 equal to 0? So we have our a will be equal to 1, our b will be equal to -4, and our c will be equal to -3. For the quadratic formula, we're going to get a negative b plus or minus the square root of b squared minus 4ac all over 2a. So we'll get out a negative 4 plus or minus the square root. Looks like we'll get out a negative 4 squared minus a 4. Our a is 1. And our c is negative 3. Our c is negative 3. All over 2a, and our a is 1. Okay, so let's go up here and clean this up. So it looks like we have a 4 plus or minus the square root. What are we going to get here? Looks like we're going to get a 16. I'm subtracting a negative plus, looks like a 12, all over a 2. So we're going to have a 4 plus or minus. That'll be the square root of what? That'll be the square root of what? 28 all over 2. Okay, so this will be 4 plus or minus, let's see, 28. 4 goes into 28. So this is 4 times 7 all over 2. Or this will be 4 plus or minus 2 root 7 all over 2. If I distribute the 2, I'll have my root as what? 2 plus or minus root 7. Or 2 plus or minus root 7. Okay. Okay. So what we have here, so let's write that. So here we have a 2 plus or minus root 7. Okay, so we have our root x equals negative 1. We have a root x equals 1/2. We also have a root x equals 2 plus root 7, and we have an x equals 2 minus root 7. If you wanted to factor this, it'll factor to x plus 1 squared times a 2x minus 1 times a x minus 2 plus root 7 times an x minus 2 minus root 7. So that's that old factor. So notice here that these are not rational numbers, so that's why the rational roots theorem did not pick these ones up. We had to use the quadratic equation to get it. Hope you enjoyed this video. We'll see you in the next one. Take care.